In the last session, we have discussed about the properties of bulk nanostructured materials such as the yield strength, hardness and ductility. In this session, we will talk about a special type of nanostructured materials known as nanostructured multilayers. And afterwards, we will think about the electrical properties of bulk nanostructured materials. The nanostructured multilayers are an important category of bulk nanostructure. What are these nanostructured multilayers? A nanostructured multilayer is a bulk nanostructure and it consists of periodic layers of different materials with nanometer thickness. For example, take the case of titanium nitride and niobium nitride multilayers. The titanium nitride, niobium nitride multilayer. Usually, these multilayers have they are fabricated by various vapor phase methods. Vapor phase methods. This is the titanium nitride layer, this is the niobium nitride layer, then again we will have a titanium nitride layer, another niobium nitride layer, and the layer thickness will be of the order of nanometers, a few nanometers. This constitutes a nanostructured multilayer. We were talking about the fabrication techniques of nanostructured multilayers, and they are fabricated by vapor phase methods, and we have various vapor phase methods for making nanostructured multilayers such as sputter deposition, chemical vapor deposition commonly known as CVD. Then we have electrochemical deposition. We have discussed about this electrochemical deposition in the last session. Now, let us discuss the special properties of nanostructured multilayers. They are very much special with respect to two features. The first one is the interface area density and the second one is hardness. We will learn about this in detail. At first, take the case of interface area density. Before going into the details of interface area density, we shall see what is meant by interface area density. The interface area density is the density of atoms in the planar boundary between the two layers of a multilayered nanostructure. It is the density of atoms in the planar boundary between the two layers of the multilayered nanostructure. I have previously drawn the structure of a multilayered nanomaterial. We were talking about titanium nitride and niobium nitride, and this is the boundary between the two layers, and we are talking about the number of atoms in the planar boundary between the two layers. The multilayered nanostructures have very high interface area densities. The interface area densities are very high for nanostructured multilayers. For example, take the case of this titanium nitride niobium nitride multilayer. A 2 nanometer thick layer of titanium nitride and niobium nitride has an interface area of 1000 centimeter square. We are talking about a 2 nanometer thick layer, and this will have an interface area of not interface area density. Interface area will be about 1000 square centimeter. The density of the material is 6.5 gram per cubic centimeter. Density of the material is 6.5 gram per cubic centimeter. It is not the interface area density, it is the density of the material. Then we can calculate the interface area density, and it is found that the interface area density is about 154 meter square per gram. 154 meter square per gram, which means you can make an area of 154 square meter with a single gram of this material, and this value is very high, and it is comparable to the interface area density of typical heterogeneous catalyst. This is comparable with the interface area of catalyst. Clearly, the best and the first application which comes into your mind will be automatically this could be used as catalyst. So, nanostructured multilayers could be used as catalysts. Now, we shall discuss the second special property of nanostructured multilayer, the hardness. So, we have discussed about the interface area density, it is found to be very high, and now we are going to discuss about the hardness of multilayered nanostructures. Hardness. The multilayered nanostructures are very hard and are resistive to wearing. They are very hard and resistive to wearing. Hardness is measured using a nano indenter. A nano indenter is used, which is a usual technique to measure the hardness of materials, and it is found that the hardness goes in gigapascals, GPa, of the order of 10 raised to 9 Pascal. Look at the figure. The figure shows the plot of hardness of titanium nitride, niobium nitride nano multilayer against the thickness of the bilayer period. From the figure, it becomes clear that the hardness increases with decrease in thickness. So, hardness is inversely proportional to thickness. As hardness goes on increasing, no, as the thickness goes on decreasing, the hardness increases, and the hardness becomes a constant at 30 nanometer. At about 30 nanometer, the hardness becomes a constant. Now, if the thickness is reduced further, if you are going to decrease the thickness of the material below 30 nanometer, the hardness will not change in any direction. The hardness will remain a constant. If there is a mismatch between the crystal structures of the different layers, the hardness is increased, the hardness is enhanced. For example, in the case of titanium nitride, niobium nitride multilayer system, as we have discussed, the lattice constants are 0.4235 nanometer for titanium nitride and 0.5151 nanometer 5151 nanometer for niobium nitride. Clearly, the lattice constants are different. This relatively high mismatch gives hardness to the multi-layered structure. There are other methods to increase the hardness of multi-layered nanostructures. For instance, if the shear moduli of the layers are having a considerable difference, the shear moduli are different, that will lead to hardness. Another way is to fabricate the multilayers with different layers having different crystal structures. If the two layers have different crystal structures, the hardness will get increased. So, the next method is to make materials with different crystal structure. Different crystal structure. If the crystal structures are different, automatically the hardness get enhanced. So, we have learned three things to increase the hardness of a material. The first one is to have different lattice constants, different lattice constants. This will enhance the hardness of the material. Then the next technique is to make a multilayer with materials of different shear moduli, which will increase the hardness. And the third technique is to make the multilayers with materials of different crystal structure. By these three methods, you can increase the hardness of the material. So far, we have discussed about the mechanical properties of disordered bulk nanostructures of different types. Now, it is high time that we discuss about the non-mechanical properties. We shall start our discussion with the electrical properties of these materials. So, we are starting with the non-mechanical properties. Of disordered bulk nanostructures The first one which we will discuss now is the electrical property. Electrical properties. A collection of nanoparticles can be made conductive or made conducting by making electrical contacts between the nanoparticles. Gold nanoparticles connected by long molecules form such a medium. Look at the figure. The hexagonal structures seen in the figure are single crystal gold nanoparticles, and the resistors shown are the conducting molecules which connect the different gold nanoparticles. Let us see how we can prepare a conducting gold bulk nanostructure. It involves the following steps. At first, gold particles are taken in the form of an aerosol spray. So, gold particles are taken in the form of an aerosol spray, and they are subjected to a mist of thiol such as dodecanethiol. They are subjected to a spray of thiol. Here we are using dodecanethiol, which is represented as RSH, where R is C12H25. So, RSH is C12H25 SH. This is dodecanethiol. So, at first gold particles are taken in the form of an aerosol spray, and they are subjected to a mist of dodecanethiol. Now, each N group SH, this N group SH can attract itself to a methyl group. So, this SH can attach itself to a methyl group. SH can attach itself to a methyl group or to a methylene chain of 8 to 12 unit long. A methylene chain. So, SH can attach to either a methyl group or a methylene chain of 8 to 12 unit long, and this provides a repulsion between the chains. Thus, the chain line molecules radiate out from the gold particles. You can see that from the picture. As the last step, a small amount of dithiol is poured onto the solution. A small amount of dithiol is poured into this solution, and a 3D cluster network of encapsulated gold particles is precipitated. The cluster of particles is made to deposit on a flat surface, and their electrical conductivity is measured. This is a method of preparation of gold nanoparticles which are made conducting. Now, we need to measure the electrical properties of this material which we have prepared just now. So, the first method is the plotting of IV characteristic. The current voltage curves of 500 nanometer gold nanoparticles, which are linked to each other by conjugated organic molecules, as we have seen in a two-dimensional array, are shown in the figure. Line A represents the IV curve of a chain without linkage by organic conjugate molecules, and line B represents the IV characteristics of a chain linked by organic conjugate molecules. From the curves, it becomes very clear that the linkages have increased the conductance. Now, let us see another diagram which gives the IV characteristics of a linked chain gold nanoparticle at different temperatures. We are varying the temperatures. In this case, see the diagram, you can see different curves, and from the curves it could be noted that as the temperature increases, conductivity increases. Once again, as the temperature increases, conductivity increases. For normal metals, we know that as the temperature increases, its conductivity decreases. And this anomalous result, as we have seen just now, could be utilized in many ways and will have far-fetching consequences. The temperature dependence of low voltage conductance is given by an equation. I will write the equation G equal to G0 e raised to minus E by kBT. G equal to G0 e raised to minus E by kBT. It is very much clear that we cannot explain this anomalous conduction by usual methods. In the equation, E is the activation energy. Here the conduction mechanism is, as I have said, cannot be explained by our usual methods. The conduction mechanism involved here is the quantum mechanical electron tunneling. The mechanism is quantum mechanical electron tunneling. And the quantum mechanical electron tunneling happens from one cluster to the next. In quantum mechanical tunneling, an electron can pass through an energy barrier which is larger than the kinetic energy of the electron. The electron can pass through an energy barrier which is larger than the kinetic energy of that particular electron. So, we have seen the electrical properties of disordered bulk nanostructures. In this session, we have learned about a special type of bulk nanomaterials called the nanostructured multilayers and seen some of their properties like the interface area density and hardness. We have also seen the factors affecting interface area density and hardness. And afterwards, we have started our discussion on the non-mechanical properties of bulk nanomaterials. We have started with the electrical properties, and we will continue our discussion on the electrical properties in our next session, followed by the other important properties of bulk nanostructured materials. Till then, bye.